integration. So let's start. Suppose suppose we write u equals f of xy and v equals g of xy, so that our good friend capital F, which has component functions g, f and g, we can write like that. So we can think of the function f, the function big F, which I see quite a lot of here as I walk around and I talk to you. I see in your notes that you don't differentiate between little f's and big F's. In mathematics, where the symbols that you use are very important, symbols carry a lot of weight and a lot of power. A lowercase f and a capital F are different things. So please do try and differentiate between them. We can think of the function that maps from R2 to R2 as being a map from the xy plane into the uv plane. Okay, so maybe we have some sort of blob in the xy plane and we carry out transformation big F and we end up with some slightly different blob. Okay, so that is one way of thinking of transformations. Yes, question? Yeah, no, it's the same, yeah. So, yeah, before I was using T for transformation, I'm using a big F for function, yeah. It's just a choice of symbol. We have, from the affine approximation, that we can linearize our potentially nonlinear vector field like that. Okay, there's the affine approximation. And recall that, as with pretty much all approximations, recall that the affine approximation to big F is a good approximation as long as we don't move too far away from that point AB. As long as we remain close to this point AB, for our purposes, we consider AB to be a point in a small region, in a very small region R in the xy plane. Okay? Okay, so keeping with this UV notation, a big sigh, and I recognized the voice sighing, and that was from close to the back. So that must have been a very loud sigh. The affine approximation. Yes, your lecturer can even recognize your voice when you sigh. The affine approximation becomes... Okay, all right. So I'm going to take that affine approximation expression that's at the top there, and I'm going to rewrite it in terms of u's and v's. Why? Well, we don't have to, but often these transformations are expressed in terms of functions like that. For instance, let me see if I can just pull up an example. Yeah, in fact, very soon, 87, 88, 90 uses these U's and V's. It's quite a common notational choice, stylistic choice. Where else? 101's got U's and V's. Yeah, so it's not something that we have to do, but it is, as I say, a common stylistic choice. Okay, so here we go. U at AB. So big F at evaluated AB obviously means that the component functions are evaluated there. The derivative matrix. So F dash is a derivative matrix. Okay, nothing new there. I'm simply expanding big F into its U and V components, which I could have kept as F and G. Why this U and V? Little f and little g are generally reserved for function names. So f of xy and g of xy. But that little picture that I drew with a little set of axes and then another little set of axes, we very rarely choose f and g to be the names of axes. So if you're wanting to think in a geometric way of your transformation taking you from one space to another space, we generally choose not to use those letters f and g because they're kind of reserved as function names. We'll rather choose other letters to be the names of our variables on the axes of that new space. And U and V are typically those names. But really it's a fairly, it's more the feel of it than a necessary thing. Okay, and now what I'm going to do is I'm going to take that vector, this first vector, this UV vector over here, and I'm going to bring it across, and I'm going to combine them. Oh gosh, I must be allergic to Wednesdays. Last Wednesday I was very lightheaded, and this Wednesday I am again. I'm allergic to Wednesdays. Let me just pause for a sec. Here we go. And yes, there was another question. Yes. So I'm not hearing well. Yeah. Oh, they're basically the same. The F and G and U and V are the same. And I was trying to see. I can kind of feel my mathematical soul can feel that there's a reason for choosing U and V. And then I was trying to articulate why. And my articulation of it is that we're wanting to use U and V as the names of our axes, as the names of the new variables that we are creating out of X and Y. And so, and F and G are not usually letters that we choose to do that, but really it just comes down to a stylistic choice. And you'll notice in a little while I'm actually going to flip back to F and G, so they're really the same. I want to carry on writing, yes? Please keep quiet while I'm listening to the question, otherwise I can't hear, yeah?
They have variables in 2 dimensions and they give out the 2 dimensions.
Yes.
How is that?
So big F would look like something. Well, let me give an example. What would big F look like? Big F could look something like big F of xy could equal x squared y plus 2, and it probably wouldn't create a picture like that. But basically, it means that you're going to put in. So for every point you put in, you're going to get a point out. Okay. So point in, and it'll be an xy point. And that'll be your point out, and it'll be a UV point. And so for every point that you put in, you're getting a point out. So you're putting in a set of points which collectively make a 2-dimensional region, and you're getting out a new set of points which collectively make a 2-dimensional region. And so you're putting in, so basically F acts on points. But those points form part of a set, and by acting on all the points within that set, you get out a new set. I don't know whether that answers your question or whether that addresses it. So your input is 2-dimensional and your output is 2-dimensional, which is what makes us have to draw rather awkward pictures like this. Because if your input if you add the dimensions of your input and your output and you get either 2 or 3, you can draw a nice picture. Because if you have one-dimensional input and one-dimensional output, you can draw a 2D picture. And that's what you have when you have something like y equals x squared. You're putting in x's, you're getting out y's, you can draw a nice little xy picture. And drawing surfaces, we're putting in x's and y's, and we're getting out z's, so we can draw a nice little 3-dimensional picture. When we're putting in something 2-dimensional and we're getting out something 2-dimensional, in order to put it onto one picture, it would have to be a 4-dimensional picture. And I don't know how to draw 4-dimensional pictures. Maybe you do, because you're engineers, and engineers can do really funky things with drawings. But I don't know how to do that. So generally, what we do is we draw the input in one picture, and we draw the output in another picture. Whereas ideally, it would be lovely if we could put it into the same picture. Shall I leave that as black scribbles there? Okay. Let's go back to green. Oh, that should be a wiggly equals. Okay, so that expression over there, we can recognize as, well, okay, there's a wiggly equal sign, but what we can recognize is that because there's a matrix there, and those little derivatives in the derivative matrix are all calculated at a particular point, so that matrix, once you plug in A and B, that will be a matrix of just numbers. We can see that as a linear transformation between that vector x minus a, y minus b, and the vector on the left, those the u minus the u and the v minus the v on the left over there. And so as long as x minus a and y minus b, as long as everything is very small, as long as everything's very close together, we can approximate what is happening there as a linear transformation. So as long as we keep r extremely small, we can use our knowledge of the geometric effects of linear transformations on the area of transformed regions, which is really what we've been after this whole time. Regions. Here, the matrix the derivative matrix Vxab, Vyab represents the linear map from your input, your R2 input, the xy plane, to R2, the UV plane, therefore the area of R dash, I need to shorten my notes, it's too much writing. R dash is the modulus. We're mathematicians, we don't like writing words, we don't like writing symbols, the modulus. The determinant of the modulus of the determinant of the derivative matrix. Sure, what a long sentence. Multiplied by the area of R. Multiplied by the area of R, which, if you'll excuse me belaboring the point, is very small. Okay, all right. Let's move on to symbols. Symbols are nicer. If we wanted words, we'd be English majors, or history, or something like that. Yes.
Can you please show a graph to see what A and B is? Like on that graph, like,
Little a and little b.
like what is A and what is B?
A and B is a point in your region. So A would be, oops, I shouldn't, actually, well, no, let me, sorry, I know I'm jumping around and you're copying down. I was going to come back again, but in fact, that with all those black scribbles, that picture is now too crowded. So basically what we have is, in our XY, we have some little area, okay, which, and I realize I'm jumping ahead here, I'm going to call delta A. And in there I have a point AB. I'm now going to carry out potentially nonlinear transformation F on that. And I'm going to get UV, and I want to draw something that's now not a rectangle because not a parallelogram. Let me draw. Oh no. There you go. There's an interesting shape. I just made that up. Okay, there's some nonlinear transformation. There will be a nonlinear transformation that does that, because nonlinear transformations do all sorts of funky things. And then that point over there will be U of AB, V of AB. It's the transformed point. Okay, and I'm going to call that delta A dash. Or I could call this R in the meantime, and I could call this R dash. I realize this delta A, I'm jumping ahead of myself a bit. So I'm right at the end of my bottom of my page here, so I have to make some space. And what we're going to say is we're going to say the area of R dash is going to equal the area of R times by the modulus of F dash. The determinant, so modulus signs, yes, but determinant in this context, determinant of F dash. The determinant of the matrix that we're using to represent the transformation, where the matrix in this case is the derivative matrix, and the derivative matrix only qualifies as the transformative matrix if we keep what we're working on very small. Okay, I'm doing a page jump. There we go. So I'm basically about to write that down just in more symbols. Area of R dash is approximately equal to, okay, all right, now I'm going to have to use some nice bright colors. What contrasts nicely with green? Did somebody just say white? Pink, yes. Okay, pink probably will. Okay, all right. So I'm going to use some nice bright colors here. Pink, here's pink. Is it because pink doesn't contrast, or because you have a problem with pink? Okay, orange seems to be winning out here. Let's go for orange. Oh my goodness, now we've got objections. Jeez, you're difficult. Sure. Okay, orange. I'm going to have some nice big orange signs here, and those are not determinant signs. Those are absolute value signs. And let me just stress that, to make positive. Okay, and then inside that I'm going to have my modulus, my determinant signs, which are, I'm doing in green. Okay, so you, come on stylist, catch up with me. A determinant of a 2 by 2 matrix is simply a little crisscross. You'd multiply two numbers, you'd subtract the product of two numbers. Determinants are just as likely to come out negative as they are to come out positive. Determinants, you do 100 random determinants, half of them are going to be negative and half of them are going to be positive. Determinants are perfectly happy being negative. But the purpose that we're putting them to is in working out areas. So we have to take their modulus. We have to take their absolute value. So there's double vertical bars there because the inside ones are the determinant and the outside ones are the absolute values. And how many of you are going to forget to do that? None. Okay, I have like one honest person. But actually, it's going to be like a bunch. Or maybe not. Maybe this year it'll be none. Oh, that's asymmetric. I can't have asymmetry. Let me fix the asymmetry. There we go. Okay. And here's a new symbol for you. Equals, and here the absolute value signs are still there, and I'm still going to do them in orange. But that thing inside gets a nice name all of its own. Well, area of R dash is approximately equal to that thing on the left, but that thing on the left is identically equal to the thing below it, therefore it's proper equal signs. That's the way the equal signs work. A equals B equals C, so it's B equals C.
But if you have to represent that as the area of R dash, it will still be approximation.
Yes.
Okay.
Okay. And that thing over there we call the Jacobian of big F. Okay. So that thing there with those curly D's. Big question. I'm multiplying, it's not cross product, there's no vectors involved. Yeah, so you can use you could use a times, or you could use even a dot, or you could use brackets, or whatever your favorite symbol is for multiplication. It's not sensitive to that like vector products are. Yes?
What function derivative are you taking? Because the with respect to x and y.
Yes. Well, it means that. It means that is a shorthand notation for the thing up there. So that curly d uv, curly d xy represents the determinant of a matrix, specifically the determinant of the derivative matrix that has 4 derivatives in it. The derivatives of the two things written at the top of that expression with respect to the two things written at the bottom of that expression. Okay, so that curly thing is... So now notice that curly D story is a determinant. So notice how those green vertical bars were no longer present in that second line that I wrote there, because that curly D story is defined as a determinant. And just for old time's sake, let's put in some little F's and little G's, but you can do U's and V's, it doesn't matter. In my notes I just happen to have F's and G's. Okay, so that curly D story is a determinant. It's not a matrix, it's a determinant of a matrix. Okay, and we can actually, it's an invertible thing, which is rather nice. What do I mean by invertible thing? The statements that I've largely scrolled past now basically says that area of R dash over area of R is approximately equal to duv dxy. In fact, you know, I'm going to stick with my color conventions here. Ugh. Also, we can actually flip it. Area of R dash is equal to which is possibly not immediately obvious. Is it obvious that 1 over that curly D story is actually, can you just flip it like you can a fraction? I mean, it's not a fraction. The symbol itself might be written with a thing and a little horizontal line and another thing at the bottom, but it's not a fraction. It represents the determinant of a matrix. Does it necessarily follow that 1 over this curly D story over here is equal to that curly D story over there? It's not immediately obvious. It is, in fact, however, true. In order to work out this one over here, you'd have to have u and v in terms of x and y, and work out 4 little derivatives and do a little crisscross determinant. In order to work out this one, you'd have to have x and y in terms of u and v, work out 4 different derivatives to that other one over there, and do a little crisscross multiply determinant. And if you compare them, you will find they actually are the same. So that is interesting, and I'm not going to prove it. I wonder, is it proven in 2084? It's the sort of thing that 2084 might prove. They get all excited about matrices and determinants and things. I should actually ask the 2084 lecturers, I don't know. Yes, okay. I'll leave it at that, and let's do an example. Which one am I doing? I'm doing that one over there, 84. What's the time? Somebody's talking to me? I heard a voice? No? Okay. Move that back to where it was. Okay, 84. What's 84? 84 is just getting us to play with Jacobians a little bit. Big F, could you please keep quiet? Is UV, please keep quiet? Where U is x plus y and V is 2x minus y. So in fact, linear. So this is actually still a linear transformation. Please keep quiet. So what I'm going to do is I'm going to find those 2 different Jacobians, the one that has the UV at the top and the one that has the xy at the top, independently, and thereby at least justify through a single example that the one is the reciprocal of the other. So duv by dxy is the derivative of u with respect to x, the derivative of u with respect to y, the derivative of u with v with respect to x, the derivative of v with respect to y. So it's the derivative matrix. Notice that I'm putting determinant lines in there. That curly D story is not a matrix, it's the determinant of a matrix, yes? Can I do it again? Okay, so basically this matrix over here is the derivative matrix of my 2 little expressions. So I've got u equals x plus y and v equals 2x minus y. I'm working out its derivative matrix, which turns out to all be numbers because it happens to be a linear transformation. And instead of going for brackets like I would if I were actually doing the derivative matrix, I'll go for determinant lines because that's what this curly D story is. A Jacobian is a determinant. And the u gets the top row, the v gets the bottom row, the derivative with respect to x gets the first column, the derivative with respect to y gets the second column. Little crisscross determinant, -1, -2 is -3. If I were going to use that determinant in a context that was involved with transforming areas of volumes, I would take its absolute value. But as it stands, it's fine. A Jacobian is a determinant. Determinants can be negative, not a problem. In order to work out the other determinant, the one that has the xy at the top, I need to make x and y the subject of those 2 little equations. Question?
Can we write determinant as like DET and then
Yes.
just to make it obvious?
Yes.
This is quite confusing.
Yes, so you would like to write it as determinant of. Perfect. Yeah. Okay, I'm going to do a little bit of like simultaneous equation-y type of things there to make x and y the subject of the equations. Question? Yes?
A bit further up, you said the area of R dash is equal to the absolute value of the curly D UV further up.
Yeah.
Where you said the Jacobian of F and AB, are you pointing at just the absolute values or is it the whole?
Just at that part there. The green part, not the orange part.
Okay, not one.
Yeah. The Jacobian is a determinant. Determinants can be negative. Jacobians can be negative. We then impose absolute values on the system if the use to which we are putting the Jacobian is transformation of areas. Okay, I am now in the process of making x and y the subject of those equations. I'm going to add 1 and 2. That'll eliminate y.
Question.
Yep.
How did that become minus 3?
The determinant is 1 times minus 1, subtract 1 times 2. So it's minus 1, subtract 2, so it's minus 3. So I don't know who asked that question. I just heard a disembodied voice. Happy? Whoever asked the question? Yes. Ah. Okay, all right. Now I'm going to eliminate x. How am I going to eliminate x? I'm going to do 2 minus 2 times 1. So that minus 2 of those. So u minus 2v. That minus 2 of those. That minus 2 of those. Minus 3y. So y is minus 1/3 u minus 2v. Okay, cool. That was just a little bit of high school maths I was doing there to make x and y the subject of the equation so that I am now ready to work out dxy duv. So determinant of, let's have a look. 1/3, 1/3, minus 1/3, 2/3. Where's my error? Somewhere there's an error. Is that actually a minus? 1 plus 2. 1 plus 2. Somewhere I've made an error. Where's my error? Or I'm going mad, which is also an option. Is that this one? Because it is 2 minus 2 of those. 2 minus... you're right. There's my mistake. I knew I'd made a mistake. It wasn't... It's v minus 2u, not u minus 2v. When I made y the subject, I messed up a little bit. Okay, now I'm going to have 2/3 and minus 1/3. Okay, now it makes sense. I could see that I wasn't going to get the reciprocal of the other one, and I knew I had to, so I knew I'd made a mistake somewhere. I just needed to find it. Okay, so that will be minus 1/9, minus 2/9, that's minus 3/9, that's minus 1/3. See how the one Jacobian is simply the reciprocal of the other. Which is interesting because I don't think it's immediately obvious that it's going to happen, but it does. Now that's just one example. Of course, an example doesn't prove anything. In order to actually prove that this reciprocal property is always true, you'd have to do a proper formal proof. I'm not going to, but hopefully that one example does at least make you confident that I'm not telling you lies. On the whole, I will try not to tell you lies. You're welcome. So why don't you give that a go, number 85. Now, from here on out, I would like you to just I'd like you to demonstrate with 85 just like I have. But from 86 onwards, you can just take it as given that the one is a reciprocal of the other. It's nice to actually see it with your own eyes with a couple of examples before you take it for granted. So why don't you try number 85? Okay, I'm saying that, but actually, do we have time? You know what? I've changed my mind. 85, homework, I'm moving on. 86. Sorry, today is a talky day for me because we're falling behind in lectures. Oh yeah, sure. The answer would be, one of them is 3 and one of them is 1/3, so it's actually very similar, it's just no minus sign. Those are the two Jacobians that you'll get. Okay, 86. It says, let f be this thing here, x, y, z, xy squared, YZ. That looks familiar. Did we deal with that the other day in some other context? Find the approximate volume of the image of a small sphere of radius r centered at these two different points. Okay, so we have our XYZ space, and there's a little sphere floating in space there. It's got radius r. We're going to transform it under F into some other space. Names haven't been given to us, but I'm going to choose UVW. We're going to transform it. I'm just going to draw another sphere, even though it isn't necessarily going to be a sphere. And the question is, what is this one's volume? So the volume of the original is going to be, it's going to be 4 over 3 pi r cubed. We're not told what r is. We've just been told it's small. And so that's V. Let me call it V nu. The question is, what is the volume of the image? In fact, let's not go for nu. Let's go for image. Image. What's the volume of the image? So that's the question. So what we're going to do is we're going to work out F dash, which is going to be a 3 by 3 derivative matrix. YZ, XZ, XY, Y squared, 2xy, 0, 0, z, y. And we're going to evaluate that at the given point. Now, of course, I've been given 2 points, so I'll do one at a time. I've reached the end of my page. So for A, my F dash is going to be evaluated at 1, 2, 3, and I'll get the matrix. Let's plug in one. I'm going to have to go onto a new page. Yeah, this is getting a bit squashed, isn't it? 1, 2, 3, what will it be? It'll be 6, it'll be 3, it'll be 2, and that's a 4, and that's a 4, and that's a 0, and that's a 0, and that's a 3, and that's a 2. And I'm going to have to work out that thing's determinant. Okay, let's slow right down and work out the determinant of a 3 by 3 matrix. I'm going to do a page jump. I have to because I've run out of space. But I will repeat the matrix. What was it? It was 6, 6, 6, 3, 2, 4, 4, 0. Thank you. Thank you. Let's work that out. Okay, there's 2 ways. Well, maybe, I don't know. But there's 2 common ways of working out the determinant of a 3 by 3 matrix. If you don't know how to do this, pay attention. Okay. Here's method number 1. Method number 1 is very nice because it works with any size matrix. It scales up. First of all, you choose any row or any column that you want. It doesn't matter which one. Typically, people choose the first row. It could be any of them. Okay? Shall we be typical or shall we be atypical? Typical. Oh, that was loud. Right, let's be typical. Okay, so I'm going to choose the first column. Okay? And I'm going to say this equals 6 times the determinant of something minus 3 times the determinant of something plus 2 times the determinant of something. Okay? Okay, don't worry about the minus, I'll explain it. What you do is you imagine that your matrix that you've got over there, your determinant, is kind of on top of like a checkerboard. And there's kind of an invisible sign associated with each square of the checkerboard, and it alternates plus, minus, plus, minus, plus, minus. So the 6 gets a plus, and the 3 gets a minus, and the 2 gets a plus. Let's say we'd chosen the second row, not the first row. Then our checkerboard would be minus, plus, minus. And then we would have had a minus 4, and a plus 4, and a minus 0. Okay? What goes into the little mini determinants? What goes into the mini determinants is what you get 6. Take your fingers and cover up the column and the row that the 6 belong to. And what goes into the little mini determinant is what's left. Cover up the row and the column that the 3 is in, and what goes into the mini determinant is what's left. Cover up the row and the column that the 2 belong to, and what goes into the mini determinant is what's left. And then you work out those little mini determinants, and you get whatever it is. We're running out of time, so you can complete that. But I'm going to show you the other method. 6, 3, 2, 4, 4, 0, 0, 3, 2. Okay, you multiply the numbers on the main diagonal. 6 times 4 times 2, and you get what? 48. Well, actually, let me not write the numbers there. Hello. Come on. 48 plus. Okay, and then you multiply 3 times 0 times wrap around 0. There's arrow number 1, there's arrow number 2, here's the end of arrow number 1, here's the end of arrow number 2. 3 times 0 times 0. 2 times wrap around 4 times 3. Here's the beginning of arrow number 3, here's the end of arrow number 3. 2 times 4 times 3, that's 8 times 3, 24. Minus, then you do the same in the other direction. 2 times 4 times 0. There's the beginning of arrow 4. There's the end of arrow 4. Come on, it's easy. Here's the beginning of arrow 5. Here's the end of arrow 5. 3 times 4 is 12 times 2 is 24. And then here we go. There's the beginning of arrow 6. Okay, all right, we've reached the end of the period. That's how you work out the determinants of a 3 by 3 matrix. It's very easy. Times, 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 done. Not. Okay, all right. I'll pause.